In this video, I'm going to be going over how to measure mean fluorescence intensity over an image stack, and I am also going to be going over our image analysis protocol for the Napoli lab. So first things first, a few Napoli lab specific things. First, we're going to have to take our images from the Axio observer, which is in Koshland. So what we do is we add Bodipy, which is going to start the fatty acid uptake process. And we're going to take one image every 10 seconds for 30 minutes. This gives a total of 180 images. And this is going to be at 20x magnification. We have done a few times where we've used the 1.6 Optivar, but for our most recent images, we've been using the 20x magnification. Once you have all 180 images taken, you're going to want to export the images as a movie sequence from Axio Observer to your USB drive. That way you can bring it back to the lab. So when you actually select export as movie sequence, you're going to get a little pop-up that asks you how many images or files you want to include in the range of your movie. And generally this is going to be images 0 to 179. So it's really useful to have separate folders for each imaging stack to make this easier on yourself. And once you've exported it, your file format should be .mov, which is a QuickTime movie. Now you're going to take the .mov file to the lab, and you're going to open these files with ImageJ, but you're going to need an ImageJ that has a .mov to image stack plugin. So I'm not sure which one is the one I downloaded, but if you go to the ImageJ located in Documents and then Conan Liu, that folder, then you will have the plugin where you can export this. If you use the regular ImageJ on the computer, you're not going to be able to export them. So after that, you're going to be able to transfer the .mov files and save it as a .tiff image stack. Okay, so let's take a look here. Napoli Labs. So first thing you're going to want to do is open your Fiji or your ImageJ. Fiji is just ImageJ. And then we're going to go find some of our files. So you're going to see here on the top I have all of the .mov files and then their respective TIFF files underneath that have already been exported from last time I was in lab. So let's just open 311 wild type 1. And we are going to open it. So you can see how the first frame is actually a blank screen. That's because this is basically when we just added the Bodipy and we haven't transferred the Axio observer from bright field to fluorescence yet. This happens just because we need to use bright field first to locate where our cells are going to be, and then we're going to switch after. So you'll see generally in the first few frames you're not going to really have a best image. And then all of a sudden it gets more clear right here. Okay, and sometimes, yeah, you're going to see those bright field images as well. So the biggest thing is we want to first remove these images that we don't want to include in our analysis. So this first gray one is definitely, this black one is definitely one we're going to want to remove. These ones, since they don't really match what we see in the next frame, I'm going to remove them as well. So to remove those images from your image stack, you're going to want to click on Image, Stacks, and then Delete Slice. So you hit Delete Slice, and now you notice that stack is gone. And now we only have 124 total images instead of 125. Now, you could just keep hitting delete slice over and over until you're done, but ImageJ also has a hotkey Shift plus R, which allows you to repeat whatever command you just input. So if I hit Shift R a couple times, we're going to see that all of these images that we don't want are going to be deleted from our analysis. So now we only have 114 slides. So it seems like the first 100 seconds or so were deleted in this image stack, which is a little bit unfortunate. Usually we want to keep it a little lower than that. And I forgot to mention, but you can navigate through this entire image stack You can see on the very bottom you have a bar that measures how far along you are in the image stack. And you can navigate either using your normal arrow keys or by using the comma and period keys, which have the little arrow carrots on top. That's the one I prefer to use because it's a little easier to reach. It's right next to M. And you can just see the progress of the time lapse basically. So first, I kind of just go through and look for any spots of interest. What I'm first looking for is kind of something that has no real intensity, no real fluorescence at first. So if you look at these guys right here, and then I just go through the stack and see that they gain intensity. So this is something that's uptaking Bodipy, it's uptaking fluorescence, and it's going to be a region of interest that I'm going to use in a bit. Another good one, so here you don't see those clear circles that we saw earlier, but you can still see that all of a sudden there's a lot of uptake of Bodipy there. So that's what the first thing I like doing, is just kind of going through the image stack. So our next goal is to select a bunch of regions of interest. So you notice we have two types of droplets. We kind of have these really mini micro droplets, all these guys right here and right here, which I have a separate protocol for analyzing. But it seems like between the knockouts and wild types they're about the same. So the one I seem to focus on the most is the medium-sized droplets. So these ones might be just a little too small to qualify for medium-sized droplets, but you can see how these look, you know, functionally much different than these guys up here. Definitely these guys that I pointed out earlier, these are going to be medium-sized droplets. And then you're going to have huge size droplets here. These are large size droplets, and I don't include those in the analysis. So we wanted to find an objective way to quantitate, you know, is it a large droplet, medium droplet, or a small droplet? So we looked at the literature and we found that a diameter of around 4 micrometers to 8 micrometers is going to be your medium-sized droplet. And doing some conversions, this is how we got this number, that an ImageJ needs to have a diameter of 12 to 25 to be a medium-sized droplet. Okay, so once we do that, we're going to get a line tool. So this line tool up here. And this is really useful because you can measure. So if I drag this across, I can measure. And you can see on the top right, under my ImageJ, so if I don't move my mouse, so it's going to be right in this area right here. If I measure that, it says length 58.6. So if you remember, our criteria was a length of 12 to 25. And so with this length, it's clearly much too large, and this qualifies as a large droplet instead of a medium droplet. But if we, for example, take this one right here, we can see it has a length of 22.55. So this qualifies as a medium droplet. And over here, these ones barely don't qualify. Well, let's see. This might qualify as a medium droplet. So with the length of 12.55, this actually qualifies as a medium droplet. We can zoom in a little bit to make sure I measured that correctly. So just measure edge to edge diameter. And yeah, it looks like it's slightly over 12. So these are actually going to qualify as medium droplets. These guys over here, however, as you can tell, are just a little bit smaller, and they're not going to qualify. So you can kind of eyeball it, but it's nice to have a reference point. So this is basically the smallest droplet I'm going to be looking at in this image analysis. Okay, so the next thing we're going to want to do is find our regions of interest. So I like to select this oval tool and just go through the image stack and just remember some of the ones I liked. So for example, these ones looked pretty good, right? So I'm going to make a small region of interest, and just kind of in the center. It doesn't need to fill the entire lipid droplet like that. You'll find that if you do that, the lipid droplets tend to move, and that's going to throw off your analysis. So you don't want to be doing that. You kind of want to, we're just taking the mean fluorescence anyways, not the total intensity, total fluorescence intensity. So we just need a little teeny piece of it in order to get the mean anyways. So what I like to do is just take this region of interest using the oval tool, and I'm going to hit T. So T is going to save that region of interest in our region of interest manager. So what I like to do here is hit show all and then remove labels. Labels is basically if it's going to have a number here or not, and it kind of obscures your vision, so I don't like it as much. Now I'm just going to continue taking regions of interest. So here's another lipid droplet, and I'm going to just hit T, and you'll see that it's saved there now. So let's just get all of these lipid droplets right here. Okay, so now those should all be measured, and then I like to just go through the image stack real quick again and make sure that all those points still line up well. So you can see at the very beginning of the image stack, we have a lot of movement, which makes the region of interest in the wrong spot. So I need to move these a little bit to the right, ideally. And it's hard when small, so let's zoom in a little bit. So I just move these all slightly to the right. That should help a little bit in giving us more accurate analysis. It's still not going to be perfect. The alternative was just to measure each region of interest individually by hand, which is what I was doing before. But not only does that take a lot of time, but it's just very subjective and not very time efficient. So here, we're basically matched up, and then by the 10th frame or so, we're completely matched up. So there's going to be some analysis there. But yeah, measuring each of these by hand would have taken so much time. Basically, you do a region of interest, and then you hit M for measure, and then you just hit next frame, and then just do that. You just measure, hit one more frame, measure, 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 and you do that for the entire 114 frames, and then you just choose your next lipid droplet, and then you do that for another 114 frames, and you do that until you measure every single one. So it takes too much time, and it's just not very effective. Okay, so let's add some more lipid droplets here. So let me get these guys. I like these ones a lot because they just show like a very clear uptake. Sometimes you'll notice that some of these guys are not really in focus, which makes analysis a little more difficult. So I want to move this a little bit to the right, a little to the left, sorry, just because it's moving quite a bit here. Yeah, and as long as I'm mostly in that range, for most of the image stack, it should be sufficient. Okay, so here I'm not actually sure if this is going to be something that shows clear uptake. Sometimes they just start bright, but it looks like this is just a bright lipid droplet, so let's take an image of this as well. And you're going to notice that all of these have really different intensities. So here's two more lipid droplets. Here's another one. And these ones I'm just eyeballing because I know they're bigger than these guys, which are at the minimum. And yeah. Okay. So I'm just continuing to hit T, continuing to add more droplets. And let me just finish this up real quick, and we're going to get to the analysis part of it. And we can use the plus and minus keys to zoom in. So you can see here, look how empty the fluorescence is, and then all of a sudden we have a lot of fluorescence. So this is another clear droplets right here, which are of the right size. These ones I'm not sure if they're the correct size, so let's measure them. That one looks a little too small, but these ones are the correct length. So let's see if they show clear uptake. And I think they're pretty suitable. So we're going to add a couple more regions of interest over there. Okay, so we have several. I'm not completely done with this image, but I think it's just a decently good time to just move on to the next step. There's so many, honestly, there's so many here. Like if I just go through here, look at that uptake. So we could just add more here. These should be the right size as well, if we take a look at them. Oh, this one's actually a little too big. Yeah, these are actually too big. So if you ever make a mistake, you could just go to the region of interest manager and just hit delete, or hit delete on your keyboard. They're too big. This one's the correct length though. So you get the idea. Alright, let's just move on to the next step, because I don't want you guys to be watching this for too long. Although I kind of just feel OCD about it and want to finish it, but it's not a big deal. So what I like to do here is I like to go into Excel. But first I like to take a picture, just so I remember what regions of interest I put, and I will have a record for the future if I ever need to redo it, or if I want to make sure that my regions of interest were good. So what I like to do in Windows is just go to Start and search for Snipping Tool. So we're going to get the Snipping Tool. This allows you to just take a screenshot of any portion of your screen. It's very convenient. I use it all the time. And you're just going to take you're just going to grab your cursor and drag it across the screen over the ImageJ part that you want. And you just hit that, and now you see it's saved this image. And now we can just hit save, and let's just save it to the desktop. We'll just do 311 wild type medium region of interest, something like that, along those lines. It's just for your own records, but I also like to put in the PowerPoint that Marta uses, just so she can see the regions of interest I chose. Now we're gonna go into Excel. Okay, now we've Excel opened, and we're gonna want to measure all of these regions of interest. And what's so great about the ImageJ region of interest manager is it can measure the same region of interest over the entire image stack automatically. So you don't have to manually do it like I was explaining earlier. All you have to do is hit More, Multi-Measure, and just keep these first two checked and hit OK. And you'll notice it has 26, so I took 26 regions of interest, and these are the frames on the left, so it goes all the way down to frame 114. If you're getting a bunch of data other than this here, you need to change your set measurements. So go to Analyze, Set Measurements, and usually when you come into ImageJ by default, you're going to have around 4 of these selected, like area and integrated density, stuff like that. We're just concerned about the mean gray value, which is the mean fluorescence. So just check that one. So let's multi-measure it again. Now I just like to copy and paste the whole thing into Excel, and I leave one space at the top. So this is every single one of the medium-sized droplet region of interest. And you'll see some of them have much different intensities than others. Like if you look at this last one, it's basically 200, and there's other ones that are only at 50 or 40. But the thing is, we've taken so many lipid droplets so that it'll even out. And the maximum intensity is 255. So this is still not overshooting what the max intensity would be. I like to go on the top and just hit Merge and Center, and then just name this appropriately. So medium droplets. Okay. So let's close the results. Now what we're going to want to do is we're going to take blanks. So I'm going to go and I'm going to delete all of these regions of interest. And we're going to look for places to put blanks, which we can use to subtract off of each of these and get a more accurate value. Okay, so there's two ways you can go about getting blanks. You can either take a bunch of regions of interest around true blank areas, like this, where it's basically as dark as possible. And that's what we did at first, but it seems to be less useful than taking blanks of cells that don't have any fluorescence. So for example, this guy right here, this is kind of just background fluorescence right here and here. So these are all background fluorescence areas, and these are ones we're gonna find more useful in our blank measurements. The reason being, if I show you an example, if we go here, I believe. No, not this one. But you'll notice that a lot of the images we use, they're going to tend to vary in brightness a lot. So the dark doesn't really change and account for when your image just keeps getting brighter and darker, whereas the true blank does. Whereas the cell blank does a little bit better. So anyways, I find it a little bit more effective to use the cell blanks. So let me just show you. I just go to the last image stack, generally, and I just find places that don't have real fluorescence. And I take about 10 or more, just so it kind of averages out. It's a little subjective, but again, it's going to average out the more you take. And again, you're just hitting T every time you want to add a new image here. And here you can use the labels to see how many blanks you've taken already. And you can even get spots that are kind of near the lipid droplets, but just not actually actively being fluorescent. Like right here would be a spot. And let's just get one more spot, I guess. Okay, so we have 10 blanks, and now we're going to hit more. Well, first we're going to take a picture of this, so snipping tool, and then we are going to take a picture of this, save it, 311 WT medium blanks. Okay, and then we are going to hit more, multi-measure, OK. And now we're going to have all these blank measurements. So you can just directly copy paste it right next to your medium droplets. And I'd like to put a title on this, cell blank. And next I type average, and I do equals average. So this is going to average all of these cell blanks together. And you just do equals average, and then you select everything you want. And this is now the average of all of these values in this row. And we're just going to drag it down. And this is going to apply this formula to each of these columns. So you see how the background intensity, look at it, it starts off around 80, and it starts going down gradually and gradually and gradually. And that's what we want to see. We want to see the background going lower and lower over time. The problem with the true blank is it normally starts off really high, and then all of a sudden it just drops and disappears, and it's just not there anymore. But I think this is a much smoother way of showing it gradually decreasing. So now I just like to hit this medium droplet column and then copy paste it over here and just change the name medium droplets minus blank. And the formula here is we're going to do equals, and we're going to select this cell right here, and we're going to hit minus and subtract the blank from it. And what you want to do is you want to add a $sign in front of the letters for your blank cell, like this. Now if you don't do that, so here's what we get if we do that. And you'll notice each of them stay as AM2 across this row, AM2. That's what the $sign does. It keeps this part static. But if you don't have this part, and then you drag it across, you're going to notice that all the values change because everything gets transposed basically. So now it's AN2, AO2, AP2, AQ2, AR2. But we want all of the values from our medium droplet to subtract from the average. Okay, so again, we're going to just put a $sign here, and then we're just going to drag the entire formula and apply it across the whole thing. and just drag it all the way down. And this is basically all of our uptake values. So this is every single medium droplet minus the blank. So you see B2 minus AM2. So this is our first region of interest. This is C2 minus AM2, which is our third region of interest minus the average for the blank. This is our fourth region of interest, third, and et cetera, et cetera. So it just goes all the way down and all the way this way as well. And this is basically your fluorescence uptake data. I like to also just put average and just average this whole column too, so I get a rough idea of what my graph is going to look like. But at this point, you're just going to input this into GraphPad Prism. So if we look at this now, we start off with an intensity of about 13, and it slowly, gradually increases until it reaches about 74. And this is when we start seeing the plateau, which means it's basically fully uptaken all the fluorescence. So this is what your graph is going to look like, but we still need the error bars, so it's still useful to keep all of these values here. Because what you're going to do next is you're going to go into GraphPad Prism, and you're going to make an XY graph with 50 replicates, which means you can put 50 values. We only need 26 replicates, because that's how many replicates we have. But you can just put whatever high number you want, arbitrarily high number, and that way you're always going to have enough replicates there. And you're just going to copy paste all of this data into the GraphPad Prism. It's going to automatically generate a graph for you, and you're going to get the uptake, and you're just going to get a really nice picture of what the uptake looks like. And after that, you can do analysis on it, which is a way for us to quantify the different rates between the knockout and wild type uptakes. And that the one we use is a two-phase association model rather. So actually, if I check my email, I could potentially find the email I sent to Marta. And here, you can see this is what your graphs are going to tend to look like at the end. You got nice error bars, and here's our uptake. And you can see wild type is kind of gradual, whereas knockouts, what we found is it's much more sudden at first. The rate is much faster, and it goes up. And this line right here is the two-phase association model line of best fit. So anyways, that is basically the basic summary of how we're going to take our medium droplet image analysis for ImageJ and measure the mean fluorescence intensity over the entire image stack.